possible to solve this problem or not. And here I would like to tell about ephemeral effect, because it is also a very interesting effect. And in the quantum mechanics of few-body system, predicted by the Soviet theoretical physicist Efimov. In this work, energy levels arising from resonant two-body forces in a three-body system. It was published in 1970. 1970, yes. It was very interesting. I read this paper of LAKAEV. It is written very interesting. He considered this case, this ephemeral case, and it means that here should be two particle operator has some singularity here. And it is written exactly so in the LAKAEV work. This is only some cases appear these things, and so we don't consider this case. It is written about 1964, and after several years, it is this Efimov discovered this effect, and Efimov effect refers to a scenario in which three identical bosons interact with the prediction of infinite series of excited three-body energy levels. Then a two-body set exactly in the dissociation threshold. I will explain what it is here. It is here in continuous. Efimov predicted this in continuous case, and any two-body particles have this spectrum. Only here, any two-body system has only resonant state. Sometimes it's called virtual state, not bound states. But three-particle system has here infinitely many eigenvalues, and these eigenvalues accumulate to zero. It is a effect. He predicted only theoretically in 1970. No, you see that after almost after 40 years, here in 2005, for the first time, the research group of Rudolf Krim and Rudolf Hans from the also Institute of Experimental Physics, University of Unispec, Austria, they experimentally confirmed such a state in ultra-cold case of LAKAEV atoms after 40 years. And there is many papers here also. They also here also partly experimental proof for the existence of the state has been given recently by an independent group here also. But after 40 years, you see that they publish it any time these results in the journal Nature or Nature Physics, and here the interest in the universal phenomenon of hot atomic gases is still growing, especially because of the long-waited experimental results. And here, okay, and few and many more for the positive stems, and this in archive, and the discipline of universality in cold atomic gases nearby the ephemeral state are sometimes commonly known, referred to as ephemeral physics. There is such kind of physics, ephemeral physics also, and also it is written in physical terminology. A ephemeral state where two body subsystems are unbounded. Two particles and no unbound, not have bound states, no, but three-particle system, three-particle system has bound state. If you predict, no, but it is proved experimentally. And so I would like to say about effective states on lattices, not so much. And in this case, three-particle Hamiltonian acts in this space. It is also some Hilbert space. It's here tensor product of two Hilbert spaces. And in this case, three-particle Hamiltonian or three-particle Schrödinger operators has this form. I consider here minus because of first time it was considered. I didn't know about the results. Any time we consider below this essential spectrum, and this operators B1, B2, and B3 it is equal in boson case and positive operators, and I consider this. The same result is true, is correct for the not positive with sign plus or with negative operators. And in this case, also, three-particle free Hamiltonian has this form because of it is also some multiplication operator, and multiplication function has this form. And interaction operator here also has this form, tensor product of two operators. I is identical operator, B is two-particle operator, interaction operator. B, it is two-particle interaction operator. No, we do not by tau k the bottom of the essential spectrum of the three-particle discrete Schrödinger operators, and by nkz the number of eigenvalues counting multiples below z, less or equal to tau k. And the Coulomb theorem describes a cumulative effect, and the three-particle was a momentum effect also for the Schrödinger operators H3k. Okay, and theorem. We suppose that H2, any H2, zero positive operator, and bottom epsilon minimum here it is. Here, epsilon minimum, and here, just the same operators. Epsilon minimum is equal to zero. It's only technical. And this singular point, singular point, it means that it is spectrum point. This is spectrum point. Really singular point. No, but there is another singularity. This point may be sometimes regular point, sometimes singular point. It means that this will be for two-particle operators virtual level and resonant state. In this case, we tell it's a singular point. The definition, there is strong mathematical definition. We should consider Bellman-Schwinger operator, and Bellman-Schwinger operator should have, for the Bellman-Schwinger operator, one should be eigenvalue. No, but here it's better to explain on that. Assume in this case it is on the first case, it is D bigger or equal to 3. Then the essential spectrum of the operator H3k satisfies this inequality. It means that essential spectrum may be this spectrum. Essential spectrum will be in this is it is only this is lattice case this, and also maybe some segments here, and here some segments. It is essential spectrum. And now it is described essential spectrum, no, but more important is here. assume D equal 3, only 3, and the operator H30 in this case, under assumption of two particle operators non-negative and 0 will be resonant point of the virtual level for the two particle operators. In this case, the operator H30 has infinitely many eigenvalues below the bottom of the essential spectrum. And for the number n0, 0, z of number of eigenvalues of the operator H3, this asymptotic is all. With the number of eigenvalues here, n0, z, tends to infinity also almost the same as logarithm model z. And because of this limit is finite. And you have more results, and it is an effect for their case k equal to 0. But here there is another result. D should be equal to 0. Then for all non-zero k, non-zero quasi-momentum k, the number in k0 is finite. For any k non-zero k is finite, but satisfy this asymptoticus. It means that, you see, it means that nk0 also tends to infinity as logarithm model k, then k tends to 0. So it is another effect, it is this effect, this another effect, it is, I call this quasi-momentum effect. This effect characteristic only for the lattice case. In continuous case, this effect has no any analogy. Here it is better to say that maybe physician people will be not very happy, but first time this kind of result is for the lattice, it was proven, not proven in physical sense. In Mattis, you know, maybe Daniel Mattis and other people from, no, he is working in Davis University of California, and Maginer, Alex Maginer, no, but he is studying not physics, no, not mathematical physics, he studied some mathematical biology, no, but Maginer told that if I can prove if k equal to 0, some results, the resistance, maybe so, if it effect, it should be true in some neighborhood of the origin. But it is not true. This result shows that it is not true because of only infinity eigenvalues maybe for the k when k belong to some surface, not some neighbor of the 0. So I call this another effect, and how much time I have? No, only maybe some words about papers related to this subject. First of them, a review of the papers related to the two-particle system. It was two-particle system. It was paper existence and analysis of bound status of the two-particle Schrödinger apparatus. Existence, you know that existence bound state exists in this, but analysis, it's if this function, wave function, is not localized, corresponding to eigenfunction, it is not localized in this case, it's not possible to say about bound status because of there is a resonance state also. So we have proved here analyticity of eigenfunctions. It means that in coordinate representation, the eigenfunction is localized. So this bound state can live long time life. You see that there is a resonance status, and the resonance status, there is lifetime of any status. Lifetime, any particle, there is some lifetime. If lifetime is infinity, it is bound status. If lifetime is finite, in this case, a resonance state. So it's possible to say any people have only lifetime, finite lifetime. So it is a resonance state, not bound state. It is, and another paper, okay, here, please, okay. Yeah, it is another paper which is published in the journal Physics R, mathematical and theoretical. Here, we find asymptotics for eigenvalues by mu, by coupling constant, here it is written, asymptotics for the eigenvalues in uk. Eigenvalue depends on mu coupling constant, k quasi momentum, and we find asymptotics when mu approaches to some, mu 0k, and coupling constant, and when k tends to 0. And here it is. There is paper, Prof, it is from Germany, and now he is working, until now he worked in Mainz University, now he is working in Braunschweig University, and Walter de Sicura Petra, he is junior professor in Mainz University, and me, and bounds on the discrete spectrum of Planck-Schrödinger apparatus. Here it is considered, we discuss the validity of the wave asymptotics in the sense of the two-sided bounds. And here we find lower bound from the number of bound states. It was sometimes bound states can be more. So lower bound and upper bound for the number of bound states. And there is another paper that is LAKAEV. It is here, this paper called Threshold Effects for the Two-Particle Hamiltonian on Lattices. It means in here just prove that if for k equals 0, this point on the virtual level, for any k appear bound states. It is proven here in this paper. Here, some papers on the, related, devoted to the three-particle Schrödinger operators on lattices, and first of them, this ephemeral effect. This effect for three-particle operators already proven in 1993. But no, so until now, no experimental results maybe appear soon for three particles. And here also another some paper devoted also for three-particle Schrödinger operators, and this paper is also related to the three-particle ephemeral effect. Here, only one it is more interesting. Here we consider not case then the number of particles not conserved. In this case, it is also possible without any interaction if there is only such kind of annihilation operator and creation operator. It is some interaction. In this case also there is ephemeral effect. Infinitely many eigenvalues. So it is so almost I have finished here list of publications devoted to the two-particle and three-particle system. Here on the two-particle system, here many particles. This part these papers published on some Russian journal and sometimes and here list of publications devoted to the many particle system. Many particle system means that 3, sometimes 4, sometimes 3 not conserved number. So I finish it.
Thank you, Prof. Okay. So I open the floor for any question or comment regarding Prof. lecture. Yes.
Your particle, is this applicable to any particles or just
Yes.
boson or fermions?
Yes, and I told here only in case boson case about effect, no, but it was no, I only told in the review of the papers. Some case we consider also here it was case 3 particles, 2 of them fermions and 1 of the bosons. In this case there is effect, infinitely many bond states. No, but if you consider only 3 particles, fermions, in this case no any effect. In this case it should be proven their existence. Bond status also, it is not easy or 3, I don't know, maybe it's possible to prove, but here no effects. In the case fermion case. But if you consider 2 fermion and 1 boson, in this case there is. And also, so I told only because of I am mathematician, I told only sometimes boson and sometimes fermion, but sometimes it is neutron. Other cases, and it is also true. This result is also true if you consider not boson, not fermion, and 3 arbitrary particles. So, and 2 arbitrary particles if you consider. And it's possible.
Because in the fermion case, you cannot have the 2 particles have the same energy.
Yes, it's true. In fermion case, this ephemeral effect is not true, and this result is also not true in the case t equal 1 and the dimension equal 1 and 2. It is not true. Should be, in this case, should be energy more, should be interaction energy should be stronger to have bound states. It's true.
Okay. Any more question? You know that you need explanation about that. Bloody?
Yes, you mentioned a lot of eigenvalues, the role of eigenvalues in the mathematics. What about the eigenfunctions? They don't. What about the role of eigenfunctions? You don't see them in your
Role of eigenvalues and eigenfunctions in mathematics. Very easy to explain. Okay, maybe in very simple case, it is if you consider system of linear algebraic equations. If for some number, if some number z is eigenvalue, in this case, this system it is possible to write a equal to some g. This system, in this case, this system, if 0 is eigenvalue, in this case, for any g, this equation has no solution. Only for some g, this system has solution. And if z is not eigenvalue, in this case, this system for any g has solution. This simple case, algebraic equation case. You can consider also system of differential equations, system of integral equations. In any case, if it is eigenvalue, no solution. No solution of what? It means it is no solution for any this G. What? You know that there is theorem. If G orthogonal to the eigenfunctions, in this case, this equation is solution. So, spectrum, it is very important in the mathematical sense also. If you are in the spectrum, in this case, no solution for any right side, where you have no solution. Or if you are, if some number not belong to spectrum, in this case, for any right side, any equation has solution. So, for any operator A, I consider here operator H is linear operator, and it is not linear operator. Sometimes it's unbound operator. So in mathematics, it's very important because of every time many people investigated some equation, linear system of equations, integral system of integral equations. Also, it's possible. Every time, if you are in spectrum, there is no solution, and only some cases there is. So,
Prof, okay. Just now you say that you are doing as a characteristic of a lattice system.
yeah.
Right. So in this case, that draw that one mod,
Yeah.
that is the lattice, right? From the E mean to the E max.
Okay, it is, I write E maximum and E minimum, it is only, but in the real I write, no, but, no, yeah. Lattice in, I have said, it is lattice only here. Okay. Yeah. Lattice should be, you know that, here, maybe, here, lattice will be this. If I consider a lattice case, particles can be only here. In the points with integer coordinates. So, and so.
Then E max is the least, least upper bound, right?
Yeah.
And E mean is the
Yes. It is only some. It is lower bound and it is upper bound for the continuous spectrum.
The two.
Yeah.
Directly.
Yeah. Because of here also in the lattice it is I don't know. I understand lattice at this, and only I understand also particles cannot be here. Only from this point should be here only. And I understand only mathematically this. No, but physician people give very good picture of what is optical lattice. Only in optical lattice is possible. No, such kind of exotic pairs, atomic pairs. They discovered on this optical lattice. And very many papers, some books appear about optical lattice because of some environment to be bound states.
In your equation, if I'm not mistaken, you use filtering factor.
Filtering?
Do you use some kind of factor? Is it filtering?
No. No any filtering here. No. Now only I consider this is not kind of a lattice. This lattice, and only I consider Hilbert space. It is space of functions defined on lattice or on the torus, because of torus is you see that it is related to lattice. Yes, can you understand? And only I consider self-adjoint, some bounded self-adjoint operators, and I investigated bound states eigenvalues. And nobody related to such kind of lattice physics, physics in optical lattice.
Okay, any more last question? All right, in that case, then let us give a big applause. Before we end up, I would like to invite Mr. Noor, acting director, to give a token to Professor LAKAEV.
Thank you very much.
Okay, with that, we end up this our seminar for this month. And then all of you are invited for refreshment outside. Thank you. One there.